He actually specifically sent me an email and told me he's not going to be in today. I won't be class today because I have an exam in materials. That happens at the same time as another class. How is it even possible? Okay, so we are live on YouTube and Blackboard, both of them. Okay. So today we are going to start a discussion on equations of motion. Let me take my jacket off. Equations of motion. Equations of motion are the meat of flight mechanics. And this is what we are going to deal with for the rest of the class. My reference for this part of the class is this book, Elements of Aircraft Performance, Airplane Performance. You don't need to purchase the book. I will make sure to create slides and share them online with you, and we will cover whatever you need in this class. And yeah, you don't need to, this is not an official textbook, so whatever we need, I will try to cover. But I will, at least for today's lecture, my reference is going to be this book, okay? Which is a very good book when it comes to flight mechanics. Okay, the first, equations of motion. Equations of motion. Okay, the first thing we need to know before understanding the equation of motion, we have to understand some basic concept and some basic nomenclature when it comes to motions of an aircraft. Aircraft can have two different motions, translational and rotational. Translational motion means we are essentially moving forward, sometimes backward. It can be curvilinear or rectilinear, which we are going to talk about later as well. Rectilinear or curvilinear. It goes back to how you define the axis of the Earth. So curvilinear is a motion on a curve. And rotation in an aircraft can be actually divided into three different movements. Let's say you have this aircraft, and these are your axis, X, Y, and Z. What is the rotation around the X-axis? What do we call that rotation? Rho, exactly. What is the rotation around the Y-axis? Pitch. What about the rotation around the Z-axis? Yeah, exactly. So all of these rotations are going to create an angle, right? When you pitch off or pitch down, your new position is going to be at a different angle. The same is true for roll and yaw, and we talked about pitch already. Okay, so the angle of pitch is theta. The angle of yaw is psi, and the angle of roll is called phi. So again, we are still in the definition area. We are defining our terms. So when it comes to the relationship between the flight path and the aircraft chord length, if you will, we have two main angles. I'm pretty sure you're already familiar with one of them, right? Flight path and direction of aircraft itself. I mean, like the center line of aircraft, whatever you want to call it. What is the main angle we have here? Angle of attack alpha. Okay. Can you think of any other way we can have an angle between the aircraft's chord length and a flight path? Horizontal angle, exactly. Now, how would that be possible? Let's call it horizontal angle. It doesn't horizontal. How can that be even possible? Okay, these are two different things, right? The angle of pitch and yaw and roll are present when you have a rotational movement, right? But the angle of attack and the other angle we are going to talk about are going to be the angle between your flight path and the line that passes through your aircraft. You can have an angle of attack when you are in a cruise condition, right? It doesn't have to be during roll or pitch.
So would be when you have a velocity in the direction of the flight path, but then you're trying to accelerate in another direction, right before your velocity vector changes. Would that be when you have that horizontal angle?
Okay, you are getting one, but I just want to make sure, because Lawson brought this up in the previous lecture as well. I just want to make sure that he is clear here. During cruise, angle of attack doesn't have to be 0. Okay, so that's the definition here is going to be different. Like the angle of pitch, yaw, and roll happens when you are rotating, rolling, or yawing, right? But you can have cruise condition and have the angle of attack, right? Which is not good. At which condition all of those other angles are 0. Okay. Yeah. So let's go back to this another angle. Let's think about our perspective. Let's back up a little and have a fresh look of the aircraft movement, right? When we are analyzing the movement of an aircraft in aerodynamics, what we usually do is we assume the aircraft is not moving and the air is the thing that is moving, right? Which is it really depends on your frame of reference, but from our point of view, humans on Earth and Earth's surface, aircraft is the thing that is moving, right? Okay, and the movement of aircraft and its direction versus it can move in this direction, right? Which is going to create the angle of attack, right? Alpha, not theta. But what happens if you have a wind gust?
Is that the situation where the plane is like trying to land and it has to land like sideways?
That's you have seen a lot of movies from there. So when you have wind gusts in some other direction, your aircraft is effectively moving in one direction, but the air is hitting your aircraft in a tilted direction. Does that make sense? So let's say we have a top view of your aircraft here. The aircraft is moving in this direction, but the wind may be blowing in this direction. This angle here is called the angle, the side slip angle. And the point here is that your aircraft is not rotating in the yaw direction here. Beta. That's, I'm sorry, hopefully next year you don't have to tell to your friends that you had to decipher my notes. Yeah, so whenever you couldn't read whatever I write on board, please let me know. Okay, so we have the angle of attack, we have the angle of side slip, and we have all of the other components. So let's think of the most general movement of aircraft. What are the velocity types of velocity we have here? We have a linear velocity, v, which can have three different components. U, if you are dealing with Cartesian coordinate system, which is the thing we usually deal with to avoid. Vj, v in the y direction, plus small w, k in the z direction. The velocity vector in every direction. And if you want to find the components, the magnitude of these components, you can actually use the magnitude of your velocity, is going to be v infinity for our cases, and multiply it by the cosine and sine of your angle of attack and the side slip angle. So your u is going to be v cosine of beta, cosine of alpha. V can be, this is a small v. You just make sure you understand this distinction. Small v, it can be v cosine of beta. So that's actually sine of beta. Sine of beta. That's only sine of beta, right? Yep. Yeah, that's a good idea. Let's do v infinity. And keep in mind, we are doing this v infinity just to make sure we don't confuse this small v with a capital V. And w is going to be v infinity cosine of beta sine of alpha. You just have to keep in mind that our agreed upon coordinate system here is z in this direction toward the surface of the earth, y in this direction, and x in this direction, right? So essentially, when your side slip angle is 0, there is no wind gust or anything. Your v is going to be 0, right? You will only have u and w. Okay. What will happen, or what other velocity is going to be present if you are rotating? Angular velocity. Exactly. Oh, I asked about your dynamics course in the beginning of class. The main reason I asked about it was that most of the whatever we are going to do today and for all of the orbital mechanics is dynamics. And you just have to make sure that you remember a good deal of dynamics. If you don't, then you have to let me know. So angular velocity, omega, has these components, P, Q, and R. And all of these components are going to be negative of d psi d theta, sine of theta, d phi dt. If you don't know, if you just joined the class, if you don't know what theta, psi, and phi are, we have them listed here. Q is going to be equal to d psi dt, cosine of theta, sine of phi. I don't really memorize these parts myself. D theta dt, cosine of phi. And your R is going to be equal to d psi dt, cosine of theta, cosine of phi, plus minus d theta dt, sine of phi. Yep. Okay. So just to make sure we understand these different components, what will be the angular velocity if we are only pitching up or pitching down? If we only have the pitch? It will only be P. Okay. What if we only have the roll? Let's go back a bit. If we are only pitching up, what will be the angular velocity? What does it mean for phi and psi? 0, right? 0, and they won't change at all, right? So d psi dt is going to be 0. So all of the first terms are going to be 0. What about d phi dt? That is going to be 0 as well, right? So P is 0. Then we are going to be left with d theta dt, cosine of phi, d theta dt, negative d theta dt, sine of phi. Phi is 0, sine of phi is 0. So you will be left out with dt dt or q. So you will only have angular velocity in the y direction, which is the pitch direction. This is what we expected. Yes. That's the idea. When you have C, that's Pi, Qj, Rk. Normal unit vector in the x direction is y, unit vector in the y direction is j, unit vector in the k direction, in the z direction is k. Okay? Okay, so what if we are only rolling? We are only going to have P, right? So your angular velocity. What if we are only yawing? R is going to be the only component. And if you have a combination of roll, yaw, pitch, all of those things, more components will show up. So these are the basic definitions you need to know before jumping into the equations of motion. So we have, for those of you who came in a little later, the idea was we have two types of motion when it comes to an aircraft: translational, rotational. Rotations can be pitch, roll, and yaw, right, in the directions. So this is pitch. This is going to be yaw. And this is going to be roll. Those of you who have had, I assume you have seen these in your Aerospace 101 as well, right? Aerospace 101, 360. You have seen it in 361 because We had a lecture on these. No. The roles, yeah, and just the direction, not all of these things. Just. No. That's what that wasn't what I was talking about. Okay, so yeah, we have the rotations. We have based on the most general velocity vectors present here is going to be v and omega, the angular velocity and linear velocity, angle of pitch, angle of yaw, and angle of roll, theta, psi, and phi. Okay, so the next step is, of course, we are going to find the equations of motion. That's correct. Yep. Omega is angular velocity. V, linear velocity. V, which is, pardon me?
Why do we use the capital?
It's just, I guess the nomenclature we use, that angular velocity. Use capital omega in dynamics too, right? For the vector, for the angular velocity vector. I don't know. I can't answer that question, honestly.
I think this makes more sense because it doesn't have to do with angular frequency or anything from vibrations. Yeah, this way it's. Not that I'm complaining. I'm cool with this because this is different enough.
Throughout this course, yes.
Better question is, why do we use Greek? Why we just use English letters?
I guess those are all good questions, but there's no way I can answer those questions. I guess we can definitely. I don't know if we can give you a Greek language degree, but if we are all familiar with Greek alphabet, that's for sure. But I don't know why they use the Greek alphabet. I guess in the 1800s and 1900s they were so pretentious they like looked down on English language. They wanted to use this like philosophy language, which was the Greek. I don't know. Yeah. But okay. So let's go back to the topic at hand, equations of motion. So we have two types of motion, rotational and translational. What is the main go-to rule or law when it comes to linear motion? What is the main law? Newton's second law, exactly. So a summation of all forces is going to be equal to mass, or let's do it. The dmv dt. Right? Changes of momentum over time. Momentum is going to be m multiplied by v. We usually assume m doesn't change with respect to time, so it comes out of the integral m dv dt. So this is going to be your for your translational motion. What about rotational motion? What should we do for rotational motion? What? Pardon me? MVR. So mass multiplied by V of R, okay, times R. You are actually, both of you, what did you say? I don't remember what you said. The d omega dt, right? Is it both of you are actually moving in the right direction, but it's not the most general format. We usually start with the most general format. That essentially will be the angular version of the Newton's second law. which is going to be your moments around the center of gravity, is going to be the derivative of angular momentum, which is B of CG divided by dt. Let me ask you this. How do we determine the center of gravity of an aircraft? Balance points. Or for an aircraft, to make it a little simpler, let's say you have two wheels. You put these two wheels on a scale, right, and take a weighted average of the values you read over here, right? And you will get a location for center of gravity. But the center of gravity location will probably given to you. I will definitely be given to you. You don't have to calculate the center of gravity. Okay, so we have these two main laws for the linear motion and rotational motion. And we want to derive the equations of motion, the most general forms of equations of motion for an aircraft. Okay. But this dv, this linear momentum, if you go back to your dynamics, hopefully, if not, if you don't remember this, then we will have a dynamics of point masses later on in the course. We will go over this, do the explanation a little more. dv over t, we can actually bring your omega here and say sigma of f is going to be equal to m, yep, partial derivative of or delta v. It can be partial derivative, or let's do delta. Your book has done delta. I'm going to do delta as well. Omega cross product v. This mainly happens because this is a material derivative, but we are not going to go into those discussions. Okay. So what is omega? What will be the solution to omega cross product of v? No, I'm not talking about what does it represent, and what is the value of it, right? How should we calculate this cross product? We have to take the determinant of this matrix, right? If you remember. Yeah, so you're going to have I, J, K. It's omega cross V, so PQR and UVW, right? And take the determinant of this matrix, as you have most definitely seen before. The determinant of this matrix is going to be WQ minus RVI plus UR minus PWJ plus PV minus UQK. So the cross product of your angular velocity and linear velocity, or velocity for that matter. What about this partial V, partial T? This itself can have, it is actually a partial of a vector product. So it will be DUI plus D small y direction J plus DW DT K, or partial W. And this all can be partials. Okay. Please tell, yes. Pardon me? You're talking about the cross product, right? I think what you're referring, it should be PW minus UR and then the minus sign. I have already put. Yeah. Okay, so we have found the components in each direction, which tells us we can actually come up with the three equations we need. F of x is going to be equal to partial u partial t plus WQ minus UR or VR. Sorry. I just make sure to let me VR, right? F of y is going to be W partial V partial T plus UR minus PW, and F of Z is going to be equal to dW dt plus PV minus UQ. So the right-hand side of all of these equations, we already have. As long as you have the angular velocity and the velocity, linear velocity, you should be able to find the right-hand side of the equations of motion to identify the motion. For linear motion, though, okay? Well, what are the forces that are present in a flight? What are the most dominant forces that are present in a flight? Your aerodynamic forces, right? Whatever those are, can be drag, can be thrust, can be lift, aerodynamic forces, right? I mean, we usually call lift and drag the aerodynamic forces, but weight is also a force that is present, but it is not an aerodynamic force. So let's do thrust plus a combination of lift and drag, which was we call the R resultant force plus weight, right? These two we can combine into aerodynamic forces. So we're going to get A and W, aerodynamic forces plus W. And you're going to see why we combine all of those two together later on. Okay. So we have these forces in a vector form, and we have these equations. The next step would be to find the components of each force, right? Components of aerodynamics force, let's call them AX, AY, and AZ at this point. But what about the components of weight? Okay, you just have to make sure. That's actually a good point that you brought up. Just have to make sure about the coordinates system we are using. This is your X, this is Z, and Y is this. Z force. Okay. That actually, you are right, but that is only true when your frame of reference is the same as the frame of reference of Earth, right? So you are moving it at the same direction as the surface of Earth. You are in a level flight that is essentially a rectilinear flight. So your frame of reference is X of E, Z of E, and Y of E, right? But we can have three different frame of references in our analysis, and we're going to do a more comprehensive discussion on this later in the course when it comes to orbital mechanics, right? We can have a frame of reference of Earth, we can have a frame of reference of flight path, which can be at an angle, right? Y, we call that A, Z of A, and Y of A. And we can also have a frame of reference that is on the aircraft itself, in the direction of the chord length of the aircraft, if you will. Okay, so we're going to call that body. Is this clear? So we can have three different frame of references, right? The question you need to answer here to be able to include weight in your analysis is, what is the frame of reference we had used to come up with yes, the flight direction frame of reference. So we have one answer for flight direction frame of reference. One vote for that. What else do you think? What is the other answers than we are that may be acceptable? That's essentially what he said, right? The flight direction. The negative. Okay. I'm with you. Yeah, we are not using the Earth frame of reference because it's going to be making everything a little more complicated, right? What do you mean by that? So what I'm guessing what you mean is, how about if we put the frame of reference on the aircraft itself, right? Is that what you mean?
Yeah, like you're looking down on the aircraft.
Okay. So that's true. We are going to use the body's frame of reference as the main frame, which means that your weight is going to have a component in each direction. Okay. So your weight force in the x direction is going to be W of x is going to be negative W sine of theta. Your weight force in the y direction is going to be W cosine of theta sine of phi. And your weight force in the z direction is going to be W cosine of theta cosine of phi, which essentially goes back to the movement of your aircraft. Like, for example, if you're pitching up, what does it mean? You will have theta, right? But phi is going to be what? 0. So we will have a component of W in the x direction and a component of W in the z direction. Let's go back to the frame of reference here. Z, X, Y, right? If you're pitching up, that's no. Z, Y, X. If you're pitching up, you will have theta. Your weight is going to be in this direction, right? And the frame of reference is going to pitch up as well. So the new frame of reference is going to be in this direction. Z, X, and let's call this Y, right? So you see your weight is going to have components in the Z and the X direction, right? it will have a component in the negative of the x direction, but it will be in the same direction as the z. So does this make sense? Okay, and I mean role is going to change as well, and so on and so forth. Is there any questions so far? I just want to make sure we are all.
You make x in the whatever direction you're picking up. Is that what you're saying?
Yeah. So your frame of reference is going to be on the aircraft. In our analysis, you can actually come up with the equations of motions in any direction. That wouldn't really matter. But yeah. So let's go back to the angular momentum and the angular velocity and try to move that a little further. Okay. So we have this equation. Who remembers what was the equation for angular momentum? Or have you seen angular momentum in your dynamics, right? Yes.
I would still say it's NPR because it's untitled.
And you are not wrong, but that's the most simplified. It is a very special form of that equation, right? Let's see that. It is going to be integral form. Yeah, that's right. It's going to be R cross product of omega R dm, right? So what Nilab is saying us is not wrong. It's definitely correct. If you have the angular velocity in only one direction around the circle, this angular momentum is going to be R squared omega, right? That's what you're saying, right? Which means that your angular momentum is going to be, your moment is going to be m R squared omega. But since we are dealing with the most general form, we are not going to use this.
Crossing R with the cross product of R.
That's correct. That's correct. That's the definition. If you go back to your mathematics, you can actually simplify this two cross products and convert them to two dot products. It is going to be omega multiplied by R dot R minus R multiplied by omega dot R. Okay. And I'm going to actually, we will do a bonus point later on in the course to prove this. Which has a very simple proof. So you shouldn't really be worried about that. One question I have though here is that what is the multiplication we have here between this omega and the parentheses? Is it a cross product or a dot product? Because I didn't put down anything here. The same question applies here as well. We have one vote for dot product. What else? Dot product?
Well, dot product gives you a scalar.
Exactly. So the dot product and cross product does not apply here because we are not multiplying two vectors. We're multiplying one vector by a scalar. So it's just a regular multiplication. it is it. Yeah. I get. Yeah, I just wanted to make sure that you are following, I guess. Okay. So if we do this, we are going to end up with a simplification of this integral. We will make this not a simplification, we just another form of this integral, which is going to be the integral of omega multiplied by x squared plus y squared z squared dm minus integral of R multiplied by Px, Qy, and RZ dm. Something that you have to make sure you are not confusing it. This R refers to one of the components of your angular velocity, but this is the vector R, which is xi, y, j, z, k. Okay, this is just a location vector. What? Okay. Let me. This also means that we can actually find the components of your angular momentum in each direction. I'm just going to write them down. It's going to be P integral of y squared, z squared, dm minus q integral of xy dm minus r integral of xz dm, right? Yep. And dy is going to be equal to p integral of xy dm, right? Yep. Yx, integral of yx. And there's also a negative sign. Plus q integral of x squared y squared dm minus r integral of yz dm. Then your angular momentum in the other direction, in the z direction, is going to be p integral of zx dm plus q integral of zy dm plus or minus. This one is a minus sign. R integral of x squared. This is z squared, y squared. This is x squared, y squared. Yeah, z squared, x squared. I'm sorry, BCG x, BCG y. This is B around center of gravity in x and y and z direction. Okay, so we have these three components. What do these remind you of? These integrals. Integral of x z dm, y z dm, all of these integrals. I see the connection, definitely. But what does it remind you from your statics and dynamics? Let me make the questions a little narrower. What was the integral of R2 R squared dm? Does anyone remember? Or dA? That's it, moment of inertia. Thank you. So all of these are actually different components of moment of inertia. This one is I of x, or I of xx, I of y, I of z. We have I of zx, I of zy, or xz. xz. So I usually confuse the directions myself. I of yz, I of zy, I of zx, I of yx, and I of xy. So essentially, see, we have everything in these equations of motions. They can be as complicated as possible. This is, I guess, the beauty of them. Okay, so we're essentially going to have BCG of x is equals to P Ix minus Q Ixy minus R Ixz. We can write this for the rest of them as well. BCG of y is going to be P Ixy Iyx minus Qiy plus Qiy minus R Iyz, right? All of those. This essentially means that your B, the vector B, is your angular velocity, which is a vector multiplied by your moment of inertia tensor. Do we know what a tensor is? No, let's do matrix then. Moment of inertia matrix. Well, the moment of inertia is a 3x3 matrix, right? Pardon me? Yep. But that's a tensor product, so it is going to be a little different. But you have the components, right? The only thing you need is to replace all of these with the corresponding moment of inertia, right? Okay. So let's go back to the main equation we had for the angular motion. M of Cg was partial derivative, a derivative of B with respect to time, right? Which means that is going to be the derivative of omega dot I with respect to time. And we can actually prove that this is equals to I dot d omega dt plus omega bcg. Okay, so we have the equation, right? We have bcg, we have i's, we have the tensor I, we have whatever we need. And on the other side of it, we're just going to have a different components of moment, mx, my, mz. So let me actually give you the equations. So you have everything you need. So mx of cg is going to be equal to dp dt I of x plus I of z minus I of y qr plus I of xz I of xz dr dt plus pq. And y cg is going to be dq dt I of y plus I of z minus I of x, right? I of x minus I of z. PR plus I of YZ XZ again. P squared minus R squared. I'm sorry that is just long equations, but there's nothing we can do about it. M, and these are M's, not mu's. Let me just make sure. You're gonna get dr dt. Again, whenever you see an r which is not a vector, that's your angular velocity in the whatever direction. I of x minus I of y, right? I of y minus I of y, I of y minus I of x, p, pq, right? Yeah. Plus I of xz minus dp, multiple dp, dt, qr. Okay, so that's it. These are the equations of motion. You have 6 main equations in each direction. 3 of them are dedicated to linear motion. 3 of them are dedicated to rotational motion. And these 3 are just the components of your weights that comes into play when you are dealing with linear motion. So 1, 2, 3, 4, 5, 6. Okay. So what we want to do now is, actually, I'm gonna give you a couple of minutes, like 1 or 2 minutes, to digest all of this information. But it's a lot of information. It is all mathematics. It can get a little confusing. So yeah, let's just think about them for a second and see if we understand all of the terminology, all of the terms, all of the notations, and so on and so forth.
That last term on the very bottom, is that QR?
QR, yeah, Q multiplied by R.
What about the very top, the very last term? Is that P?
PQ. Yeah.
I like the linear ones a lot better.
Q. So omega is actually PI QJ RK. So Q is the component of angular velocity in the y direction, which is the component, the angular velocity in the pitch direction. So if you have a Q present, you're pitching up or pitching down. Does it make sense?
We get that from the omega, right?
Omega, yeah. That was, yeah. Let me clean this side of the board.
And R hat, that's R. This vector, right?
Pardon me?
R hat is the vector.
R hat. R, that's actually R with the vector sign, right? It is not a unit vector. This is I hat, right? It's a unit vector. Yeah. Just wanted to make sure we are on the same page. Let me ask you one question before we move forward. And this way I can give those of you who need more time to digest this, more time. I was watching my YouTube lectures online, like to get a feedback from myself. And I was mostly writing on the board. So I wasn't talking to the students. What do you think about that?
I like when you have a board. It helps me out.
Okay, so it is better than presentations then. But if I'm presenting something, I have more discussion with you guys.
Yeah,
Huh?
I like both, honestly, but like whenever I'm visual, so whenever you're writing, like that helps me
Huh.
the most. And
Okay.
then I can write it down too. and
You can
then
follow, yeah.
Yeah, it helps me follow.
Okay.
It's nice to have it up there so we can talk about it. So it doesn't just fly by and like forget like what was what specifically. Once we get it up there, we can talk about it.
Yeah, then we can give it some time to talk about it. Okay. I'm a board guy. Yes, go ahead.
Are they on Blackboard still, or is it just on YouTube?
Right now I'm still doing both of them, right? But I'm going to move to YouTube completely eventually.
What's your channel?
It is Mustafa. I will send you a link.
Okay.
If you actually go on Blackboard, you will get a comment with a link and everything. But I will post the videos. I will do that this weekend, hopefully. I will just post all of the videos in their corresponding folder, right? So when you go to the like introduction folder, you will see all the videos. I mean, I started doing this at the middle of the class, so you will see the review of aerodynamics and the equations of motion. Euler. These are called the Euler equations. Yeah. You think? I guess during his time. Yeah, you have a lot. Euler, I guess if it wasn't for Euler, we would have there wouldn't have been any mechanical engineering, right? And all of us would have been just farmers or whatever. I mean, your point is actually correct. I think that someone else would have came along. Okay, so I guess we have had enough time to digest these equations and have a couple of minutes to rest our minds. And yeah, so let's apply these equations to the specific types of flights. And as you probably would guess, we are going to use the simplest form of the flight to do the analysis, which is always the case. Okay, so the first thing we wanna go over, the first type of flight we wanna go over is the most general, a steady motion. Okay. A steady motion. That's a good question. Does that make a difference? We have one yes, one no. Does whether the flight is supersonic or subsonic make a difference in these equations? The equation of motion. No, not a steady motion. Your point was about the general equations of motion. Yeah, the whole things. Okay, so we have two yeses, I guess. One no. One soft no. Yes. The answer is no. Okay. But what? But why? Why is the answer no? We derive these equations of motion assuming we already know the velocity distribution. So we already know what the velocity is. right? We have already made all of those assumptions, calculated the velocity profile, then derive this equation. So that's that the velocity is given to us here, right? And since we are dealing with a whole aircraft, you are essentially dealing mostly with flight velocity, right? We are not really concerned about what is going to happen on a wing. Does this make sense? Okay. So let's do the steady motion. So this is a macro perspective, if you will, compared to a micro perspective that deals with like whatever that is happening, the flow separation on a wing. Yeah, a steady motion. What is the first thing that comes to your mind when you hear the word steady motion? Zero changes over time, right? But in our equations, we are not really dealing with acceleration. We're just the derivatives with respect to time, right? So du dt is equals to the rest of the ddt's, and all of those are 0. Okay, the same is true for d theta and d phi. So we can actually reduce these equations of motion to these. I'm just going to write them on the board. So for the first one, w sine of theta, which was wx, negative w sine of theta, plus all of the aerodynamic forces in the x direction, is going to be equal to m wq minus vr. Okay, and keep in mind, w and v are components of linear velocity in z and y direction. Q and r are components of angular velocity in y and z direction, right? For the y, we have w cosine of theta, sine of phi, plus a of y, which is going to be equal to ur minus pw. And for z, we are going to have w cosine of theta cosine of phi plus a of z is going to be equal to pv minus uq. Okay. We can also write this for moments as well. I'm going to write them here. M of x. Let me actually ask you to give me that. What will be m of x? We have 4 people in class. 3 of you will just volunteer to do this. IZ minus IY QR, exactly, plus IXZ PQ, right? Okay, what about MY? Pardon me? No, every moment is around the center of gravity, right? So it is always mcgx, mcgy, always, right? It's the same thing. We are just applying. We are like simplifying these equations for a steady motion. Okay, so ix minus iy, iiz, pr plus I xz p squared minus r squared, right? So what about the last component? Iy minus ix pq plus negative qr. So these are the 6 main equations of motion for a steady flight, for a steady motion. Okay. So let's apply this to a helicoidal flight. What is a helicoidal flight? Yeah, that's me neither, honestly. So this is this type of flight, right? You start from here, you're just pitching up and rotating. Helicoidal. And it's called the helicoidal flight, but I'm not sure. No, it is like this. Pardon me?
Is that the same? Is that helicoidal?
Yeah, as long as you're moving in this direction, right? What was your question?
So I was thinking from the perspective of blades that are taking off, that would be a helicoidal geometry.
I would assume the airflow pattern will be a helicoidal pattern, right?
Yeah, the blades would be talking about.
Yeah. But it is, again, it is a macro perspective here. So we are looking at the aircraft that is moving in this direction. Right? The air movement patterns. Okay, so let's finish this. A helicoidal flight. What do we have in a helicoidal flight? We are only pitching up, right? Okay, so how should we? Yes. We are turning and pitching up. That's correct. So the components of angular velocity is going to reduce to these. d psi dt in a very general form, so non-aesthetic motion. d psi dt, d psi dt, cosine of theta, sine of theta, and then d psi dt, cosine of theta, cosine of phi. What was the psi angle? That's correct. It was yeah. So in a steady flight, d psi dt is not going to be 0, right? Because like especially in a helicopter, that is still a steady flight, but the psi is changing over time, right? And PQ and R are gonna be this. I guess we are R over time. Let's stop here. Let's start with the steady motion, and then we'll come pick back up the helicoidal flight in the next lecture on Tuesday. I will also post new homework on Tuesday. Tuesday is going to be February 16, right? Yeah. And new homework will be posted on Tuesday. And we will actually apply this to different flight patterns, different flight conditions to make it a little more, to make you guys a little more familiar with the whole concept of equation of motions. Okay? You're all present, so you don't have to.
What'd you get? You got 8.16? Yeah, 8.166.